types of heat flow we're going to look at is conduction. And conduction occurs in a solid. And I've just got a question that here's one I prepared earlier. A little question that we can think about that certainly conduction would be the issue. So we've got a wall made of iron, and then there's this magic number, which we've looked up on somewhere like Engineering Toolbox, which relates to iron and how much heat it transfers, and I'll explain the units in a second. So 70 watts per meter per degree Kelvin, degree Celsius or degree Kelvin, doesn't matter because it's a temperature difference. It's 50 mils thick, surface area of 2 meters by 3 meters. On one side it's 150 degrees Celsius, on the other side it's 80 degrees Celsius. And the question is going to be how much heat flows through the wall. So first thing we need to do is let's get an understanding of how heat flows through a wall, and then get a formula for dealing with this sort of stuff. So basically what's going on is we've got our wall. Effectively on this side of the wall it's hot, so 150 degrees C, and on the other side it's cold, 80 degrees C. Now 80 degrees C is not cold. I mean, if you dunk yourself in water that's 80 degrees C, you'll say it's not cold. But the fact that it's colder than this side means that the heat will flow from the hot to the cold. So the heat flow is going to always be from the hot to the cold. And what happens in a solid is all the atoms in the solid are fixed. They can't go anywhere. There are all these molecules inside your solid. And what happens is when something's hot, that means that those particles that are hot move a bit. So these ones on this side are jiggling around quite a lot because they're comparatively hot. And effectively, these ones bump into, pass their energy onto these ones. So these ones are going to start moving a bit. And as you go across, they're going to keep on moving the ones across until the ones on this side are moving at the same speed as the ones on this side. And at the same time, we'll put some of the heat energy out into the cold air on this side. So as this one side is hot, it transfers the heat across, not by any particles moving, just by the energy being passed from one particle to another. So the energy, the particle that's on this side stays on this side, the particle that's on this side stays on this side, but the energy is passed from one to the other. And we have a formula for calculating that, and the formula is Q equals Ka delta T over S is the formula for this. And we need to know what all these bits are. So Q is the rate of heat transfer. So how fast energy is being transferred from one side to the other. And it's a rate, so it's a time-based thing. So it's going to be measured in watts, or maybe kilowatts if it's a big thing. But watts is power, joules per second. So that's what we mean by rate. So heat shifted at a particular rate. A is the surface area. Okay, so whatever the surface of this wall is the A we're going to be working with. Delta T is, as usual, change in. Remember that triangle is always changing. Change in this case, temperature. So surface area should be in square meters. It's a change in temperature, so it doesn't matter whether you use degrees Celsius or Kelvin. They'll both work. I put that degrees on the wrong side of that. In the right place, that makes more sense. Okay, so delta T is the change in temperature, and like I said, it can be in either Kelvin or Celsius because it's a change in temperature. It doesn't matter when you subtract two temperatures, they'll come out the same whether you're using Kelvin or Celsius. K in this case is the thermal conductivity, and that's measured in watts per meter degrees Celsius or watts per meter Kelvin. And the only other thing missing is S, which is how thick the wall is. So S is the distance across the wall. So thickness. And that'll be in meters. Okay, so that formula tells us how fast heat is transferred through a particular substance. So K will change from substance to substance. So you look that up in tables. So for iron, it's 70. For different substances, it'll be different amounts. So things that conduct heat well, it'll be a big number. Things that are not good conductors or insulators, it'll be a small number. And this enables us to calculate how much heat is being transferred. So when we come to this formula, answer this question, we just go Q equals Ka delta T over S. Bung the numbers in. K is 70. Area is 2 by 3 is 6. Change in temperature, 150 to 80 is 70 degrees. And the thickness, 50 mils, so 0.05 of a metre. And then we grab a calculator, push all the buttons, and what do we come up with? Let's turn the thing on first, it always helps. On 270, so that's 70 squared. My calculator 0 doesn't work too well, 70 squared times 6 divided by 0.05 equals 588,000. So 588 kilowatts. Okay, so that's quite a lot of power. Measuring things in kilowatts is an awful lot, but 6 metre wall is a good sized wall. Iron transfers heat really well, and it's got a 70-degree difference across it, so it's quite a big thing with quite a lot of heat going on. And you'll be losing heat. If you had this set up, you'd be, or maybe transferring heat, maybe you want the heat to go, you're not trying to keep it in. The heat transfer would be 588 kilowatts. Okay, so basic idea of conduction is it occurs through a solid. So the particles stay put, but pass the energy from one side to the other. The heat transfer goes from the hot side to the cold side, and this formula enables us to calculate how fast that heat will be transferred. Okay, conduction.